Okay, one more example of quotient ring, and this one is to show how quotient rings naturally appear in geometry. I'll take a little bit of liberty here. I mean, I cannot quite prove everything that I state, but I'll try to be as precise as I can. So let's look at R equal to the two-variable polynomial ring. Polynomials in two variable x and y with real coefficients, let's say. So you can think of these as a set of all polynomial functions on the plane of R2, real valued. And by functions, I mean just real valued functions, right? If you give me a two-variable polynomial and give me a point in the plane, I can calculate its value at that point and I get a number. So this is a function from the plane to real numbers. Okay, let's take this polynomial, simple polynomial, fxy equals y minus x squared. This is an element of my ring. If you look at where this polynomial vanishes, meaning all points in the plane, this is a function on R2, right? So I can look at all x comma y where fxy is 0. That's just the parabola, right? The standard parabola. All x comma y says that y equals x squared. Now by a polynomial function, a polynomial function on my parabola P just means restriction of one of these polynomials to P. Means a function that is given by restriction of a two-variable polynomial to P. Restriction of a two-variable of a polynomial in R. Okay. So each G in R defines a polynomial function G restricted to P on P. So what's the difference? So, and I let S be the set of all these. So let S be the set of all polynomial functions on P. So what's the difference between R and S? The point is that different polynomials, when you restrict to this parabola, can become the same thing. For example, if you restrict the function y minus x squared, this is the element of R, right? If you restrict this function to your parabola, what do you get? You just get the zero function, because by definition of the parabola, this function vanishes everywhere on the parabola. Right, so this function f and the zero function, they are two different things in R, but they define the same function in S, you see, because they define the same function on my parabola. Maybe I should make that remark. note that f restricted to p is 0. So what have I got here? What I have got here is I have got a map alpha from R to S. And it's a surjective ring homomorphism, I claim. What is this map? It's given by, you give me a two-variable polynomial, and I just restrict it to my parabola, and I've got a polynomial function on my parabola. And by definition, all polynomial functions on my parabola are these guys. So it's an onto map, of course. Verify that this is a ring homomorphism, and there's nothing to check really, because the addition and multiplication on both sides are just addition and multiplication of pointwise addition and multiplication of functions. It's the same thing. So this is a surjective ring homomorphism. The question is, what's the kernel? I don't know why I called it alpha. Maybe I should call it psi, right? To have my setup, have it set up for my first isomorphism theorem. So we have this surjective ring homomorphism psi from R to S. What is the kernel? The claim is that the kernel of psi is, so you already know something in the kernel, right? F is in the kernel. And if f is in the kernel, all multiples of f is going to be in the kernel. The claim is that this is all multiples of f. And proving this would require a little more than what we have right now, so I'll skip this. Skip for now. But this inclusion is clear, because when you restrict f to p, you get the zero function tautologically. So f restricted to p is 0, which means psi of f is 0, which means that f is in the kernel. So all multiples of f are also in the kernel. So if once you know this, you know that psi induces an isomorphism from R mod f to S. This is by first isomorphism theorem. So in other words, what's the upshot? The upshot is that the set of polynomial functions on P is this quotient ring, Rxy modulo the ideal generated by the function that defines the parabola. And it turns out that studying these rings is a very, very powerful algebraic way to study geometric creatures like P. So if you want to study the parabola P, you want to study a lot of property of P are reflected in ring theoretic properties of this ring. And this actually generalizes. I mean, instead of P, you could have a surface or their higher dimensional cousin, what would be here called an affine algebraic variety. And you would study similar rings to understand those geometric objects. And these rings in those contexts are called the coordinate rings of those varieties. Okay. So study. I'll just make a remark and stop. Ring theoretic properties of this S reflect geometric properties of P. Okay, and this generalizes. So this sort of quotient do naturally occur in geometry. They occur as set of polynomial functions on curves and surfaces and things like that.